I'll get back to you. No worries.
But just get a couple cups.
I know.
Stay.
That's cool. It's always sort of like.
I can really plan this out. Yeah, I think this is it.
Yes.
But you know, you have to do it right from that. But just because, handing out material, going up the aisles and throwing stuff over, you're all sort of in this general area. But, the next.
I'm sorry.
So.
Hey, folks who've been in the valley. We're a smaller group now. Fill in. I don't know if you want to sit in the first row, but at least like this sort of middle area.
Good job, Mark. I'm on the front row.
Good.
Good, thank you. Don't get too comfortable.
It's okay.
On the board, there's in the front? Sir? Thanks, Scott.
I saw one of those.
Yeah. He's gonna start.
Is this in there?
Sure.
No, that's, is it squeaky now? Crazy chipper. I woke up and thought there was so much in there. It's like, oh my God.
Are you going?
What was this?
The bed.
Oh.
It's like, oh yeah, I was like, I didn't know.
Okay, because I wanted to get copies of the safety handouts for the boys.
Oh.
Someone else.
My floor.
I heard a bunch of problems.
It's a lot.
What room were you?
226 and right down from there.
Too loud.
Yes, you were. Oh my gosh, I kept looking at my house.
I'm about to say you need to be louder.
Your life, I kept figuring
I think that was me.
It was somebody with a man's voice.
All right, I guess I can't deny it.
I don't know. Try.
I'm gonna follow my chair.
No, it's not. I'm sorry. I didn't read it all. That's correct.
That's right. Is that right? Let's get a sign right down there.
Do we have to check anything, or is that good? We're good. Okay. I can't help it. Thanks for coming. And here we. It was on the schedule. I think it's called Inquiry in Action. Is the session? It's actually so it's Inquiry in Action at middleschoolchemistry.com. So those two resources we'll be doing. And I guess we probably should continue sort of like in an NGS. We'll still look at those performance expectations and the foundation boxes to make sure that what we're doing kind of makes sense as far as those standards go. Anybody have any questions? NGSS presentation, anything come up? They discussion this morning with folks about what they'll really think. Like some people were saying, oh man, another set of standards comes along now and respond to it somehow. But then, some people are saying, well, it's not going to be teaching. You might have to write down like a new standard. That's not a big deal, I don't. What do you think about that? Do the standards, the way we've talked about them so far, I got to change my teaching style or my way I present, or is it? Oh, okay. Wow. So what grade do you teach?
First grade.
What about the first grade NGSS? I mean, let's see, what are we looking
With like ocean planets and then something else. And I do like sort of child. Yeah, or not.
Okay.
I mean, for fourth grade, I was going to be teaching every single one of my in Michigan as I'm teaching right now.
Wow. Okay. So for some folks, it changed. Content different. Oh, okay. Why do you say no?
Ours all seem to be the same. The thing that I'm concerned about being sixth grade, making sure that sixth grade covers what we need to cover and not moving too much for seventh and eighth grade.
What do you mean exactly?
Well, with the NGSS being middle school,
Oh.
I would hate to leave an eighth grade teacher dumped on with a bunch of. So that's my concern. Is just making sure we communicate and that we all cover.
Right. That seems like a tricky part of some of this is coordination of 7th, 8th grade to look at that whole thing and see who's going to do what. Well, maybe you all do to some extent and build on each other. Hard to say how you split things up. Well, I don't think yesterday we got a chance to actually look at the site. It's not there yet. I just Googled NGSS, and we didn't do this yesterday, did we? Look at this exact site, or did we? Did I have it up there for a second? Oh, well, I just want to show you the way you navigate it in case you haven't been here yet. Different ways to get into the standards. You can view them by disciplinary or by performance expectation. I always go in by topic. That's just my preference. It's easier for me. Then you get to this thing, which doesn't look very helpful until you scroll down. I'm gonna go to second grade. I would just pick, grade 2, of matter, and then you hit search, and then and there it is, and then you click on it. Is the page with the second grade structural properties of matter. I like sometimes looking at it or if I'm going to print it out, I make it a PDF. So if you're, if you need to go to the standards and you haven't done it yet, that's by topic, and then you pick the grade and the topic you're interested in, and then go that way. So let's start. That's like the main page. These sheets from yesterday, the set of standards. If you don't, I'll just bring it up on the screen. I'll just go back to what I just took away. We're just going to look at the second grade structure and properties of matter standard. we looked at, let's see. Oh, yeah. 1 and 2 PS1, 2. This idea that you could categorize objects by, and that you could test them and see if they're good for a particular purpose. Like that was that engineering thing. Do the activity really? I mean, you did the sorting, but this idea of maybe constructing a boat using paper, plastic, and aluminum foil, what would be better and why, and how could you combine them to make a good boat? Anybody have any ideas, just off the top of your head? Well, like if you're going to do tests, I was thinking you could do like how. So you would have kids, maybe you'd work with them to design a test. How these different materials act in water. What other tests could you do? Good, strong boat. Any ideas? What do you think?
On it, have a partner hold it, or somehow advance that and see how much
The paper before it's like folded into the shape of a boat or anything, like a piece of paper, a piece of plastic, or would you?
It'd be a good place to start.
Yeah.
Then you could start putting them together or whatever.
Eventually, you're gonna come up with some little structure that you help the little second graders or first graders. I guess second grade standards. They come up with a little boat, and then I guess you put it in water. Then you could add stuff to it, maybe, and see how good it is. Like, well, what's the standard approach? Everybody puts pennies in, you see who can make the. It's not a competition, but you want to see if you're. Right. So, all right, so it's involved this engineering thing, and maybe, what seems to be on these boats, but the taller your sides, the better you are. Because if you have really shrimpy of your boat, you put a little weight in, and water's going to start coming in over the side. At tall sides, it's going to give you a smaller boat, smaller surface area of your inside your boat. And there's a balance between how tall your sides are. But anyway, you're going to notice that the taller the sides, the better. Anyway. These standards. How about, even if you're wearing name tags, which you're not, the names are so. Could you remind me, Amy? Sorry. Let's look at one more second grade standard. How about 2 PS1-4?
Argument with evidence that some changes caused by heating or cooling.
Great, let me just go there really quick. I mean, you read it beautifully. 2, structure and properties of matter. Let's see, yeah. Okay. So we're talking about this very one the other day. Construct an argument with evidence. Some changes caused by heating and cooling can be reversed and some cannot. Grade. Now, when they use words like construct an argument with evidence, these are only second graders. What are you talking about? But, you would have to, to be able to see something, interact with something in some way, and then conclusion based on what they saw and did, right? I mean, it's kind of for a second grader, but they use the same science and engineering practice language for every grade band. So it seems like maybe to ask a little kid to construct an argument seems like, right. What do you, am I putting words in your mouth? I mean, does that seem like kind of advanced first or second grader to do? Right, but they're never going to see the standard, right? So you know what you're asking them to do is to interact with substances and see if it with you, with your guidance, and then eventually they can come to some conclusion. So, do you have any ideas? Again, we're not trying to come up with one activity that nails the performance expectation, but what could you have kids do to at least begin a set of experiences for them that would get them to see, what does it say here? Some changes caused by heating and cooling can be reversed. And what are they looking for here? There's red print that gives you some, and sometimes the clarification statements are clarifying, but sometimes they're not. But anyway, Mark, I remember. Mark, what's one possible approach here? You,
Suppose with reverse melting and freezing the water. Now, irreversible even cooking the levels. Burning or something.
okay, yeah. Here's a actually for teachers. Have you ever done this type of thing where, I mean, maybe it's not an obvious concept, but the standards now think it is, that some changes that happen are reversible, and some, once they're done, they're done. Have you ever done anything like that? Well, could you just say what you've done loud and clear?
Different properties of matter and with water, you know, I give them ice cubes and I say, okay, what can you do? So they'll rub it or they're, you know, go on it or look at it or whatever. So they'll do different things, but then we say, okay, I'm going to take all that back, and then I go and I do, it's like, change the back.
Right.
So sweet.
So the people who wrote this important concept for young kids to get the idea that some can't. Have you ever done the some can't version? No. Yeah, that's true. Point just so one thing out to you really quick. I think, whoops, I almost did it again. This clarification statement is okay, but it's a little weird. You're probably a good reader, college student and all. Statement for 2 PS1-4.
Examples of reversible changes include water and butter at different temperatures. Examples of irreversible changes include cooking an egg.
Okay, I've looked at this a lot. Does anything jump out at you as being, they're talking about irreversible changes, and they have here could include cooking an egg, makes sense, freezing a plant leaf. Isn't that reversible? Yeah, I mean, I don't know. I live in D.C. It doesn't get that cold, but the plants with the wall, those freeze, and then they seem to be okay. I don't know. They thaw. Then
It's well, it's not the same.
you think? My
It was off.
oh, a leaf that's off the tree.
If you stick it in.
Ah, that's what they mean. See, we clarified the clarification statement.
I don't think that one either, except, I mean, it's gonna look the same though, right? I mean, no, it's quite different.
You know, you get frozen
That's
plastic
for
that
sure.
Yeah.
messes it up.
You know,
It's coming back.
the tricky thing for me in this one is that if they're edging toward a chemical change, the egg, I think, but the freezing of a leaf is not that. You know, it's physical change, and right? I don't know. I think this clarification. I think it's mixing two ideas.
Does it say that in it?
Includes, you know, cooking, which is usually a chemical change, which is just not a chemical change. I don't know. It seems like you could muddy the water a little bit. But the other one that I think is weird, what's your name? will, it says heating paper. So if you go like this, and then miraculously it's back again. So that didn't seem irreversible. It meant burning paper problem. So anyway, for the people who are going to deal with second, I think I know what they're trying to get at, but the clarification statement, isn't quite what it could be. Now, I don't have a set of activities for us to do with this new performance expectation. But what you've been doing sounds like the right thing. Any other ideas? Like, let's say if you, a what? Could you explain what you do with the crayon? Right, but you looks like kind of a puddle, looks liquidy, and then you say, look, I mean, they can describe it, and is it the same color as it was before? Yeah, it just changed sort of like. And then when it's liquidy, do they play with it? Got it. Oh, okay. You can see that it's. And then what happens? Do you put it in the fridge, or you just let it come to room temperature?
We've done both because they want it. If it's something dirt, and if it would, we get them kind of a cast iron with them.
Hey. And then do you do like a wax paper or what? Then once you have the crayon, once it gets hard again, do you try to draw with it or anything? Does it work? That's a neat idea. So that's a reversible change. That melt freeze. I mean, I guess crayons have a pretty room temperature. Any other ideas? Other irreversible. I mean, they say cooking an egg. I don't know if you'd want to do that in class. Maybe any other thing you could do with second graders about the irreversible changes?
I'm trying to set concept of why it change color. Sunlight, beams, and
Oh, I see.
light, chlorophyll, leaves. So I was trying to.
Oh, interesting. So would that be in fall time for will change for that leaf, right? That's never going to get green again. That's nice. Any other ideas? No, not at the moment. Yeah.
I do it in the 7th grade. I mean, I light a candle, and the whole everything they describe what's physical and what's chemical, what is reversible, irreversible. I don't know if second graders, if they'll catch that the match is not
Done. Right.
That's what I try to, trick those 7th graders into saying. Just observing and tell me, let me know what's going on, because they've all seen candles and lit them or close enough to it to know what's happening with the wick.
Yeah. I guess. What do you think, Mark?
Another one that changes the stations. One that I use is just easy bake down.
Say it again. Easy.
bake down. Yeah, I mean, whatever. Maybe else. Purple. I don't know. But anyway.
What is the point you're trying to get across? Not here. I mean, in doing that with the kids.
You can't go and separate the flour and the oil.
Right, exactly.
Right. Once it tastes terrible, or your little cookie or whatever.
Hey, ours turn out great.
Oh, do they?
Yeah.
That's a neat idea. What grade is that for?
It's 7th grade, it would be advanced. Like little kids.
Oh, I bet. So they probably go crazy.
Yeah. They
So,
would.
where do you source your incandescent lights?
Wow. No, go ahead.
There are two. I've done that. That would be good.
Yeah. Does it? Can you have a microwave in your classroom? Is it? Oh, really? Yeah, that's a neat idea. And that gets right to this idea that, you know, it's not the heating. I mean, it's a chemical ultimately causing it to be irreversible. It's the heating that's, you know, but I guess the standards writers didn't want to go that far. You know, they just got with, you know, heat reversible change, and sometimes it can cause some reversible changes. And I guess they're thinking that in later years, the reason for that will get filled in. You know what I mean? Because it's not just something's really going on there to make something irreversible, and it's really it's a chemical reaction that's happening in cooking. But you could either go there, you know, how you run your class, what you think your kids can get out of it. But it's not the words. That's the reason. Okay, let's do some activities, and we'll start with. How about? Oh, let me go to. If you flip over, if we go to a 5th grade structure and properties of matter. Does everybody have access to it, or? All right, so I get. Well, I'll go here. So 5th grade, right here, property of matter, search, around here. Okay. Do you guys remember what we did yesterday? Let's see. Yeah. Yeah. It was 5 PS13. Make up materials based on their properties. We're going to have listed for us to do here. Oh, okay. Let's start. Could somebody read? How about Scott? Could you read 5 PS11?
Develop a model that was too small.
In middle school, Kevin, in the middle school, we were looking at that drop of water on on wax paper. Here is a different way to do this. It's actually more complicated. It's kind of fun. Let me grab some stuff. Do you guys do an activity where you put M&Ms in water? Have you ever done that? You get some neat effects. How about if we do, let's see, groups of either 2, and I'll hand out some materials like yesterday, you know, just so you can work together. Let's see what else I have here. Break up. You 2 and you 3? Okay. And you guys, you want to be a little group of 2 here? Yeah, some of these M&Ms are relatively newish, and some are really old. So I don't know. Pop one in your mouth. Yeah, out on the website. Yeah, the website is basically, it's the book. Has some multimedia associated with it. View this water source.
Thank you.
You're welcome. Can you hand this back to those guys? Get some more water.
You're smart.
How about, thanks. I got this one. Take us actually out of here into middle school, into Inquiry in Action. And in Inquiry in Action, activities, chocolate. And serious M&Ms, yeah. Basically, by kids looking, well, we're not going to M&M out of the bag. Each person can do it. And just look at it. We'll describe it really quickly. Now, this is the what you want kids to do in 5th grade is to begin to develop, what did this one say? Develop a model that matter is made of particles too small to be seen. There's so many ways to do this. This is just one of many possibilities. So they look at this M&M, and can we get some description?
Katie?
Katie.
It's round.
It is round, and by round, do you mean like a...
Not really.
Disky-ish?
Yeah, disky-ish.
Sort of like two frisbees back to back, kind of? Yeah. Anybody else? I mean, it's shaped Latin sphere, maybe. You wouldn't say that, but well, what else about it? It's got a pretty smooth surface, at least to the naked eye, right? On it. Somebody in one session that we did once, a teacher said it has an E on it. It must be an E. I said, wait, that's an N.
W.
Anything else? What's the big obvious thing about M&M's? Yeah, they have these really. How about this? If you guys take the M&M and bust it in half, as best you. Oh, it doesn't have to be half exactly. Just break it so you can look at the cross. It takes good strength. Can you do it or no? Ugh. Oh yeah, use your resources. Good.
Just stab it.
When you look at it on the inside, what do you see? Brown stuff, right? We know that's chocolate. What else about the? How about the coating? What does that look like? Thin coating. Is there any color to the coating? Like obviously that it always had. But can you see anything else? White. So for 5th grade, to that idea that there's some white stuff there. Wow, I didn't see that before. What could that be? What do you think that is? You know what the white stuff is? See, in the yummy candy coating? Well, you know what? I think they actually do use form of that for the M. The M is like carrageenan and wax or something. But for that candy coating, the hard stuff is, take another guess. Yeah, it's mostly, sucrose, sugar. So let's see, have you guys ever or eaten M&Ms and the color comes off? And you know the old hands is a big lie? Because, I mean, some of it does. Look at that a little in depth. So, you guys, you have a plate, or actually not so many. You've got, I think, 3 plates that have circles on them and 1 plate that does not, with no circle. And if you pour water in here, we're just going to see how it is wet. You know, if you guys touch it with sweaty hands when you got out of the pool, that's one thing. Water in the plate that fills up the bottom of the plate, and just put an M&M right in the center. And it doesn't have to be so deep as to cover the M&M. It just needs to cover the bottom of the plate. Put that M&M in there. All right. Oh, sorry, a brand new one. Any color you want. But do you want?
That's like the best though.
You can hand this water to them. There, you can have your own.
Now we don't.
So you guys, oh, you want to put it? It did. Oh. Oh, something's going on there, right? All right. Ask kids. Well, I'll ask you guys. Do you see anything already? I mean, they've only been in there. But what do you see? How about? Okay.
Katie.
Katie, of course. Katie.
The M&M's bleeding color. Leak out.
Okay, so it looks like the color is leaking out or bleeding. How about, what do you actually see? Like, describe, look down at the M&M. Like, what would you say the colors? Yeah, it's kind of,
Bleeding out.
yeah, the color's spreading out away from the M&M or dispersing, right? So, you know, what do you think, grader? Oh, sorry, we're talking fifth graders. Might they say it's dissolving, or what do you think? Yeah? Okay, so we have it. Okay. So a fifth grader recognize this as dissolving. So now we have to, if is to develop a model to describe, sorry, that describes matter, oh, I can't read. To describe that matter is made of particles too small to be seen. I guess somehow, if you're going to use this as a starting point, you're going to maybe, the kids would have already known that water is made of molecules at this point. It depends what the background is to this. And what would you say if the M&M is made mostly of sugar, let's say, with some coloring, and the water molecules are in the water? How about what? I'm sorry. What? You need big. Well, what would you say is going on here? Any idea? Like, you can say, but if we're going to say, start talking about particles, what's doing what?
Water particles and the color sugar particles.
Yeah, and but the water seems to be causing the particles to break away. Vince, what do you think?
Because it's the molecules of the water move more than molecule. Because those water molecules are moving, even though we don't see them moving, bouncing around and hitting the sugar, which is a solid, and breaking it up.
More or less, yeah. I mean, you could have this discussion with kids about the approach, because all they want you to do is begin to develop a model that's some particles. Well, how can you do that unless you look at some phenomena, right? If you look at what we did yesterday, or look at an M&M, you need some context to begin this conversation. It's just a context. So you could start saying that water molecules gas with sugar molecules, and in some way, we like to use the term attract, some way grab onto them and I don't know, wrestle them enough the other sugar molecules. And that's a pretty sophisticated idea that you get at. So then, now I have to tell you, I don't know if any of you were, if I had this conversation yet, but when we did this and the book, in place at the time were called the national, which didn't want teachers to go to the particle level at the lower grades. Was that clear, what I just said? They didn't, they see really until after middle school, to 9th grade before attempting a particle or phenomena. That seems too late to me. But we are, the ACS, the national organization, to write things according to what the standard said at the time. So now, and they were in place for a long time until this set of standards came out, written under the National Academy of Sciences, which now says that new research shows begin to understand a particle level model of matter. So what do I do? It's not just my, it's not about me, but I don't have level explanations for kids in inquiry and action like I have because it was done at a time when they didn't want you to go there. So we could talk about what you could do to help kids understand what you just say it, right? You wouldn't say the water has particles or molecules, the sugar molecules. Well, what could you do extra to help kids? Because what are they going to write it down in a little 5th grade notebook, and then you're done? Well, what could you do? How about Mary Beth?
Do an activity like simulation.
Okay, if you could find, the internet's probably covered of showing that substances are made out of particles. You could go to middle school chemistry, and that, although that wouldn't show you this exact thing in context, it wouldn't the sugar that's on an M&M in a 5th grade friendly way. But you could try.
My lesson is each state of matter.
Mm-hmm.
So that's experiences. I'm going to do this. But I think this would show them that. And I what solid with them again, all of it, with their own body. So do this, and then actually make them get up and have molecules backing up solid, or backing like a liquid around them, and kind of maybe attracting, grabbing them off, and making them now the solid coming apart.
That sounds great to me. Does that
Am I on the right track?
sure seems like it? That seems great. If you had a group of kids and they were the solid sugar, so they're, I don't know if 5th graders would hold hands or not, or whatever. To move in place, right? A little bit, because they're a solid, but they're still in motion. And then the water, I don't know if that's mayhem or if that, you would control it and. Right.
But I was thinking in my head I could have, you have the M&Ms full of blue paper, so the water as they come, and so now they're seeing the blue now scattering about too.
Nice. It makes it. The blue is most available, the color, because it's on the outside. So you could even have water color, and then you can have other ones that take sugar if you want to. Or I don't really know the water is grabbing both at the same time. I don't know how that works. But
it would show them that it's the taking out, because as I'm sitting here, we're not touching it. It's now all the way to the end of the plate. It's going out further, but some of those blue ones are still probably hitting.
yeah, there's actually, there's 2 processes here. We only really use, but there's this other thing, diffusion. Once something's dissolved in water, it's going to concentration to where it's a lower concentration just from random molecular motion. So, that might be something you might revisit this to talk about diffusion later. 2 processes going on here. But like I said, if you want to just focus on the one, you get really far with your idea of modeling it that way. Any other ideas about what you could do beyond saying this is dissolving and saying that molecules are interacting with the and breaking them apart. That's one great way, I think. Anything else? Any other model-y thing you could do?
Maybe try using hot water or cold water to see if that, if it or slower.
Yeah, that's a great idea. In fact, that's where. Wait a second, Scott.
Good job.
I want to ask you about something, like, how would my students feel about this? And I know I have a few that would say, I understand what you're saying about the molecules moving, but in all honesty, maybe it's just some, that's why it's spreading out, because if the M&M was warmer than water, and the heat out through the water, that's why the dye is moving. And they may say, there's no way, given this amount that are spreading that.
Okay.
And I mean, honestly, I wouldn't have an answer for them. I don't know.
I mean, maybe you would just say, well, I had this water and these M&Ms in the room together. Temperature. They're both at room temperature. There's nothing special, at least as far as thermal M&M versus the water, so they're the same. In fact, if you want to investigate that, let's do it. We'll try some. We'll put this room temperature M&M in cold water, room temperature water, and hot bins, and maybe that'll help, answer the question. So let's do it.
But, that's what I'm thinking. It's not going to, it won't take one experiment
Oh.
to convince somebody. Full ones. And, like, 'cause I would shock this with the bubble and the little half-pint water bottle.
Mm-hmm.
Get those molecules, air molecules moving.
Right. Yeah, it is surprising.
So, it's a really question.
Right.
It might take a full week of these kind of things.
I mean, that is a great. I guess that's teaching, right? Is you got to do things many times in different, and what they're coming to their preconceptions and how they look at the world, and you need to get all the way to the molecular level if you're a fifth grader. It's hard enough when you're in graduate school.
Where does the switch flip? Developmentally, argue that maybe a lot of them it's not. You could use a magnifying glass, use that. And then it would be, where does those macro models, kids bouncing around,
Right.
Little pin, and then where does it really really?
Right.
Everything's made of little vibrating.
Yeah. That switch probably doesn't flip in everybody, ever. But be different. Something will go, I get it, eventually. And experiences or, 10 years of being
Then you
science
screwed all up. What?
Right.
Wait, what do you mean there's a big distance?
Right. Exactly. It's funny. There's a guy who used to work at the ACS who he was a great. He said he was so frustrated sometimes at the end of class, after he worked, say something like, "So there's no such thing as a dirt molecule." And the dirt is made up of little things that we've been talking about all year, and kids, it's a different, obviously. You guys, if we're going to do an experiment with, we need some hot water, and we need some cold water. So, how many little groups we have? 1, 2, 3. Are you guys 2 groups? 4, 5? So let's get me and 5 people to go get some hot water. I'll show you where we can get it.
I got my water.
Oh, it's going to be enough. It's going to be pretty close. All right. I'm going to run and get a little bit more. If you want to get up and walk around, go ahead, because it's going to take me a minute. You can if you want. Just, pull. I did not do it. All right, you pass those out.
I will.
Beth, how did you know right off the bat that
I listened to you, Jay.
Oh, yeah,
that was so great? No, you know where we can get it?
Always stay
Over
dressed.
where the food is. Right. And just be careful, it comes up pretty hot.
On your own.
Okay, we'll be right back.
Yeah. I can't stop you from it.
Almost.
What a joke. Around, yay. Oh, I see what you're doing.
Yes, guys, he did not make it.
Well, how about you go from there? I know another source. I'm going to go into 3/4 full, so it's not too crazy. Thanks a lot.
You saw
And these screw on, they just push them down with the other way. Yeah. It's not obvious.
Get out of here fast.
I think I'm going to use your container.
I hope he doesn't stop me there.
I told him not to.
You come here often?
I don't know if that worked.
The hot water?
One. But I like.
If I can start with a bagel.
Hey, how you doing?
Start with a bagel and then have a never-ending supply
No.
of liquids and good.
Hey, I've got some ice too. So you know, with fifth graders or with any age, even youngins, always. I mean, you guys probably do this. Take the opportunity to have you design the experiment, because it'll be a lot better for them and why they're doing what they're doing than if you just give them a sheet that says do this, do this. We always spend a fair amount of time in Korean Action and in middle school chemistry with the test. So let's do it. So how would we do this, you guys? Scott actually brought this up. You brought up this idea of temperature, and so did the nice lady. Nancy said also maybe put them in a see if temperature matters. Maybe we this whole process. So I'm talking to the kids here as a teacher, and I'm guys like, Will, how do we set this experiment up? What should we actually do? One thing to talk about, another thing to do it. So what should we do?
Tray with hot, cold, room temperature water.
3 different plates and we're going to put cold water in each one. Okay. And then what will we do then?
With some M&M. And how long it takes for the diet of each. Yeah.
Okay. Sounds good. Now, should we put the M&Ms in at the same time? Okay. Color M&M? What do you think? How come? Well, but just yeah. Nice. That's the reason. Very, very good. Whenever I have this discussion with the conclusion first without the reasoning. They say because you want to control all variables. But purpose of that? It's because there might be something about the color that would affect green. Like you said, dissolves faster than yellow. So if you have a green in one area, it's not going to tell you much about whether temperature matters. That's going to tell you something of, well, it's going to. So, you see, we try to have this talk with kids over and over again. Like Will said, we're going to have 3 plates. We tried to mark them this. You could work with, we pre-marked them for you guys. But that could be a whole discussion about how we're going to reach whether temperature matters. They're going to say, well, you just look, and the one that spreads the most, they're close, you know? Do we care? Is there any way to measure this? Some kids will say you can put a ruler and look down and actually take a quantitative measure. That's pretty cool. Well, no kid is going to say this, I don't think. But use a overhead transparency with a look on it or something like that. You know, there's lots of ways. But one way is to put concentric circles. We just used, I don't know, a cup, I think. I think I used the bottom of the cup for the small circle and the top. But you can do it in lots of different ways. Okay, so then we would really have controlling the variables. So should we use the same amount of water? Ron, should we use the same amount of water in each one?
Probably.
Well,
Trying to be a 5th grader.
yeah. So if I'm going to engage you in this, would it make sense just to put a little bit of water, let's say a small amount of cold water, but a lot of hot M&Ms and see what happens? Would that be a good way to do this test?
Well, 2 weeks ago when you were teaching us the scientific method, you said that variable.
Right. But the amount
One variable.
Right. But on this one, just like the color in this experiment, the amount of water might matter. So all we want to do is see if temperature add any other tricky thing to this. So we want the amount of water to be the same. So the only temperature of the water. Okay, so let's run this test. But before we do, cold water. Just like yesterday, I'm not ready. Yeah, I'll put some ice in a cup. You guys can add a little bit of room, make it cold, then pour it in your plate. Okay? But don't add ice, because that solid in there would be a big variable. Your legs, you can come up and get a cup of ice, or we can hand them around. Either way. Are you going to be ice distributor for everybody? Right?
I'd be dead.
You're coming.
Okay. I got a little bit.
Right? I teased. I don't know if we need. Here, can I add? Oh, yeah, let me add one more. Just another quick point on this one. You want. You know, for us here today, we can do this very qualitatively, where we know one's room temp and one's going to be hot. But if you want to have kids measure, you could have them take the temperatures of the water if you wanted. If you want to give them practice reading with them, you could use a graduated cylinder or a beaker and know that you're using the same volume, temp and cold. So you could make this quantitative if you wanted. Will mention what they take to reach a certain point. We're not going to do that, but you could do that. We're just going to look at them in absolute time. All right, run your experiment. Good luck.
I don't. What we did was
Oh, yeah, that never happened. My fault. Just be a little careful with the hot water. It's pretty darn hot.
That's the hot one.
Oh, look at it. There you go. Oh, you're bad. Yeah, you should put all your waters in at the same time to treat them exactly the same. M&Ms at the same time. That's okay.
Yeah.
Also, that's okay. And the other thing you could do is use 3 concentric circles. I didn't say, but the kids kind of grab onto each other with a. But don't worry about it now.
Oh, yeah.
Yeah, start
Worth talking about already, or no? Yeah. Yeah. No, okay, just because, move along a little bit, and just like yesterday, we're not spending the kind of time, obviously, they would be writing down all their observations, making drawings. We could, I don't know, do you guys do that in class, have kids take pictures? Yeah, I'm so behind the times, that way, pictures. Would you ever have kids make videos of something that, wow, cool. Yeah, so modern. Results. How about Ron? What do you guys see?
Well, I mean, they're premature because we had cold water over here, but it sat a little longer while you were talking. So it may not have been that I did.
Excellent.
So, but even though the room temperature and the ice water was really close, you could see a difference.
Okay. Okay, the hot water. This was an easy case where we probably should have, just because they've got enough. Take a darn good guess that the hot one would probably dissolve faster. How about your group? What were your results? Right. And how about the cold room temp? Okay. Is the amount of dissolving on the hot water greater? Okay. I'll try again. Is there a bigger difference between the hot and room temp than between the? That's what I'm trying to get. Okay. Any ideas about why that might be?
Probably a greater temperature. With cold water, you just swirl around room temperature water. Hot water probably that's a lot hotter than
Right. That's probably true. That there's a greater difference in temperature between hot and room temp. Because cold, is just near zero, maybe like 4 or 5 degrees. So it's a 15-degree difference. Whereas that water was hot. I don't know what that was, but 70 degrees centigrade, it's a 50-degree difference between that and room temp. So a good difference between hot and room temp than there is between room temp and cold. But let's get back to Jill, does understand anything about particles? And could you try to explain, put the M&M in the room temperature water to begin with? And I came up with an explanation. I think that water molecules were interacting with sugar in some way, attaching to them or knocking them away, and that caused dissolve. Now we have a new phenomena that even happens. It seems to happen faster in hot water. Can you say anything about particles to help us make sense?
It's happening faster than.
So particles are moving faster in the hot water, and that's causing the dissolving to happen more quickly. What is that, though? Why would faster moving particles make something dissolve faster? Say it again?
Heat energy?
Well, that's a term, but what's actually happening? Particles. They're moving faster, but why would that cause faster? Because they're hitting them with more force, maybe? Is that one possibility? Any other thoughts on that?
More molecules.
Oh, so you think it has something to do with if the molecules are moving faster, more water back into sugar molecules in a given period of time. Does that make, Will, you buy that? Yeah. So, Amy, how you doing? So could you then model your kid model, or would that be too dangerous at this point?
No. I talked to, I just put the freezer, and you have to go back into a solid state, and then I'll say, so they amp it out, and yes, so they get a little crazy.
Right.
They think the concept. So when I would say this, they know they get a little bit shake a lot more than when they're just like.
Okay, if you heat them up. So basically, if you can take this phenomena and use what kids about particles and motion, then maybe you can get to that point where they could even model happening faster that produces a result. Like if you increase the motion, you get that's the cause. You may get an effect of increased rate of dissolving, and you might be able to. And I think Mark did it. He said that they're just striking more often, and you might say more often and with greater force. Even the solid, you put that M&M in hot water, it's not only the water molecules that are moving faster, molecules are going to be moving faster too and loosening up their attractions to each other. So there's a lot going on. Some of that, I think, with fifth graders. Did you want to say something? No? Okay. Let's keep rolling with it. Oh, is there like a Lego version of any of this? Like we talked about people themselves, but is there another way to go, another model that if you don't feel comfortable having the kids, what could you do with stuff? Any thoughts?
But I don't know how you can do it to get it to distract.
It might be tricky, but if you had kids, you showed maybe the sugar as being Legos. I don't use Legos that much, but having some little pieces attached to each other, pieces of a different color, I guess, that are water, and if you go, you bring them in, they separate, but then you have kids bring them in really fast. Maybe kids film, do that, and it's a pretty decent model of what's going on, possibly.
Area, but could you do something like in those rooms where you put them all the time, and like you put like 5 blue balls on top of all these come in. Now, if no kids come in, they never move. But if you have one kid in running around, the blue balls will be moved somewhere. Then you put 20 kids in there with, birthday cake or whatever.
Right.
And then they all move, then all of a sudden, you might not even be able to find they're
Right.
going to be.
It's a neat idea.
I don't know.
Yeah.
I'm not there. How you could.
It's hard to tell, exactly at this point, and you're thinking, what represent, or,
Kids are a liquid that comes in.
Yeah.
I don't know.
it sounds like that's got definite possibilities. It would be really, really fun. But you got this modeling, yeah.
You could fill your whole classroom with all.
Yeah. What fun would that be? What else do we have? Oh, for 5th grade. Oh yeah. Look at 2. I want to talk about this one real quick before we go on to 5 PS1 2. That must be on the other side. Wait, what am I doing here?
Okay, from the beginning.
Okay. All right. Scott, could you read, it's grade 5, Structure and Properties of 5 PS1 2.
Measuring graph quantities to provide evidence of change of heating equivalent or mixing substances. The total weight of matter.
Okay. This is a classic. Anybody, this is a mass idea. So if you have, well, does anybody just want to say with kids, if you've had a substance, you change it, check to see if it weighs the same, or if you have 2 things and you weigh them and then you mix them, they weigh the same, or you do a chemical reaction, you weigh it beforehand, weigh it after, that it should weigh the same. Of that? No? Yeah, what have you done?
So, let a ice melt on in a container and it's on a scale.
Okay.
And with the vinegar on the top of the glass, and you actually prove while it's on the scale with it. After it's melted, you just sand let it go dry. That last one,
I don't want to. I'm having a big problem with this one, trying to find chemical change. Now, Mark, right?
Yeah.
And
Mark off.
okay. I brought a scale here. Okay. And if this works, it'll be nice. Let's see. Now, Mark, I'm not saying you're wrong about your vinegar and baking soda thing. Get that to read the same mass with a balloon on the top. Please still work. Adam, are you going to help me by putting it on that document? And, we got a small enough group that it could come up if we can't get it to work. But. Some cool. Here they are. These are these little self-inflicted. Oh wow! Can we see? No, I was just seeing if we could see the reading of the numbers.
I mean, there should be a top light on the projector.
Here's I don't know if you guys ever get these from a dollar store, but they're like little self-inflating balloons. They've got roll up. They have a baking soda on the inside and a little pouch of citric acid solution. And what you do is you break the little citric acid solution packet. Oh, really? Yeah, they sell them in the dollar store, if you have dollar stores here. Mustache, or a heart for Valentine's Day, or happy birthday, and they come with a stick. Darn, it looks good, but you can't see the numbers. I'll give you time. So let me, I'll show you how this works. But they're completely sealed, so, wow. So here, you can just pass that around if you want.
Yeah. Are they a buck a piece? Is that what they typically are at dollar store?
That's a good. They're probably sold in. I don't know if they're sold individually or in packs. If you guys want for some, you can contact me and I'll just send you some.
That's cool.
Yeah.
Special for a buck.
No. What's that?
I said especially for $1 a piece. I'm like, there's a
Yeah.
a month, you know.
Usually we use them one for every kid, but you know you might want to use them and pass them around.
Okay.
But anyway, Mark, here's what happened with me when I tried to do this. I put one of these on a scale, and I checked to see the mass, and put it on the scale, and immediately the apparent mass, according to the scale, and it just continued to go down. It lost about, I can't remember how many grams, maybe, I can't remember, about 1.5 grams or something. I was like, whoa, what's going on? Container, those dump containers, and I did it and less. Then I put it in a closed container, and I did it, and it went down a little, losing mass. This thing is sealed. We have them for months, completely inflated. So there's nothing escaping, you know, we don't think, and yet the buoyant effect, this thing increasing in volume, sitting on a scale, makes the, let me show you. Adam, way to go. Oh, sorry. You know, maybe I'm taking too much time with this, but looking at about, well, you can read it, right? Now I'm going to activate it and put it on. Yeah, but let's use this very one. So 15.75, that's it. So I go like this. And what a bummer. This would have been great. But to any kid in his or her right mind, and it's not. So anyway, all I'm saying is that sometimes these, you get an idea that you think, when you test it out, physics and messes you up. It's the air on this thing that now has the same mass but more volume is giving it an. So, and Mark, I tried this with the famous in a what kind of, like one of these kind of containers used yesterday, and I put baking soda in a balloon, floppy, and then I connected the balloon to the top, and I stuck it on the scale, and then I lifted the balloon and as soon as that balloon began to increase, if I had it on a scale, a sensitive scale happened, but not this, obviously.
We just had a glass straw.
That's, I think, for anybody who wants to try that, I think that's to counteract that being lifted by the balloon. So
I
you're,
miss that.
Use up bigger, heavier glass
Thank
flasks. It's harder for that balloon to that much bacon. So you're not getting the balloon like super huge.
I don't think so.
Harder to get the buoyant effect or something more.
But
Right.
does it still move? You know,
Sometimes you might get a temperature damage. It's not like you're seeing the boat. It describing an event kind of thing. You show it to them and say, well, we know contribution what's going on here, why
Right.
it's dropping and it's not supposed to. So that's
Be-
a lot of using something like that.
Right. You're just entering a whole different topic, though. But you could use them that way. But that would get you into a physics idea, which is pretty interesting. Let's do another activity. To clean this one up, you guys, carefully pour off the M&M and the liquid into the dump container. I'll give you some paper towels, and if you give the plates just a quick wipe, they clean up. Thank you. And can you pass me the set for that?
No personal here.
Oh, you give me the whole set. Thanks.
it's just one of the came up with this.
Yeah, but you know, we did it based on something that we saw years ago. You know, are you familiar with them?
Oh, yeah.
Right. But we go right. You know, I did a workshop weeks ago, and the co-presenter there said, what would happen if, so she wants the kids to finish that, happen if I, and she wants kids to say, change the temperature of the water. What would happen had something in the water to begin with, like I made it a salt solution or a sugar. And if I, and she wants kids to say, I don't know, tried it in milk or liquid completely. You know, so for young kids, it's not hard to come up with testable questions that way. One thing that the standard is have kids understand how to develop a scientific question. And that's one way to do it. Use common language and an experiment that's easy to see. What would happen if? So you can try it. This next one we're going to do, everything back in the bag, like just stack the plates up, close up the little zip closing, and stick it all in, and we're good. I'll pick it up.
I don't know if you
Oh. Thank you. And then, hey Mark, yeah, if you pass those up. Come on, get with the program. Jeez. Oh, I'm swishing the. Whoops. I'm just getting a bag of stuff. This is like a continuation of. We did the clear colorless liquids on different papers. This is kind of a related activity, but using a different. I should say, if you want to be fancy. Some of these maybe want to closed as test as well as it could be, so just maybe be aware of that.
Here's another one.
Oh, thanks.
Yeah,
That's fine for this one.
Yeah, no big deal.
I'm going home really soon. Yeah, but you want to blow up your laptop.
Right.
No offense, Katie.
Yeah, none taken.
Okay. All right. You guys, you can take all the liquids out of the bag. You should have yellow liquids that are all identified, and then some yellow liquid, A, B, C, yeah, and a blue. So here's what we're going to do. The idea behind this one is that it's related to what we did before. In this case, we've got liquids. We took those exact same clear colorless liquids and put a drop of, or maybe two coloring in each one. And we just want to see, instead of putting them on papers to test them, we're going to see what they look like when they're mixed with blue. So, you know, because yellow and blue, we should see some combination of greenish. So on this one, I can't remember, but I have to be honest with you, I don't think we spent with kids talking about how to test, like use the same amount of, if we're going to combine blue water with yellow liquid, amount of blue water each time when we combine them? Yes. Should we combine them the same way? Yes. Look for how they're the same or different, and see if we can see the different substance properties. Like in this case, it's a kind of a weird property, how it mixes with another liquid. Often think about. The classic one is how a solid dissolves in a liquid. Other liquids too. So we'll check that out. So here you go. I'm going to... Maybe we'll do it this way. And could you just hand one back? To start, you guys, if you look at this little sheet, we just, the sheet is laminated it. So while it's sitting on your little table there, if you the 5 drops of blue water in each of these circles, it's say one here, 5 drops of blue water there, 5 drops of blue water there, and 5 drops of blue water there. The ones that are identified, water, salt water, alcohol, and detergent, not A, B, C. So you're, oh, I know what I did. I was going to say it'll be a miracle if I find these toothpicks and I found them. So now, could you guys put 5 drops of each yellow liquid, this liquid spot? Oh, nice. Yeah, let me give you enough. Yeah, right back to that. And then, if you want to be, you can hand that little set to that group. Exactly.
Yeah, I want to see like. Thank you.
You're welcome.
Okay.
At this point, if you're working with, you know, youngins, you could make some observations right off the bat here. You know, some of these liquids, even though they're different, they know they're different because they're labeled. Similar, the way they sit on the laminated chart here, but some don't. So here's what we're going to do. You guys, we're going to move blue water to each case. And the way you do it, if you hold your toothpick kind of parallel to the surface of this chart, this laminated chart, and then just drag it until it just touches the yellow liquid, and then pull away. Don't stir. Yeah, so just drag it over and let them touch, and then oh, these should be 5 drops each. Is that 5 drops? Wow, it's so strange. I'm gonna give you a little. Oh, okay. Just drag that across. Yeah. And then here's absorb. We're going to drag it till it just touches. No. I probably should have used that document camera. Then add some more alcohol if you have a problem, because it looks like it all went away. Just touch it. You can do. You can get there.
And then what's this?
Nice. Obviously, you already did these. Did anything interesting happen with the alcohol, or did it just mix? Just. Mm-hmm. Okay. Do you guys have now? You probably would have. I mean, you could give them a yellow, blue, and green, a colored pencil, and have them make some observations. They would write as well as draw. It's another set of. And just determine what A, B, C, and D are. Yeah, I think so. Or maybe you could just put a piece of wax paper over the whole thing instead of laminating if you're not into that.
Once you laminate it, they last.
Yeah, right. Paper probably wouldn't be good. So now you guys have to figure out how you would run your test so that you can determine the identity of A, B, C, and D. What would you do?
Yeah.
Yeah. Hey, Hannah. Book floating around anywhere? So you know. Oh, do you? Okay. I got it. Okay. Thanks.
Maybe he'll autograph it for you.
No, when I want to see what the answer.
Really doesn't want to touch it.
Yeah, it's pretty neat. It's going okay. I'm just looking for the answers. I can't remember where they are. Okay, and this one you got to end when. Good. You guys, I know the answer's in here, but I can't find it, but even if I don't, we'll see if we have unanimity. That means like everybody. Using the defining test or must be here. Identities of the A, B, C, and D? You think? Okay.
Yeah.
I got it. You think you know? All right, let's just see. And if you do this with students, if you decide to do any, it's just like yesterday where, we put these in these little dropper bottles because it's easier to travel with these. In here in the book and on the website to be in little cups that you would give the kids. In a way, it's not good because on the alcohol, they could smell it. Yeah, so you could prepare this, and like somebody said yesterday, it will last a long time.
This is great to see. I get a Dixie cup
Mm-hmm.
in my 6-hour refrigerator.
Mushy.
It was mushy and
Yeah.
so it was.
Yeah. What was A? What do you think? And we'll go in a weird order. What was D?
Water.
It's C?
Alcohol.
Alcohol. Then by process of elimination, detergent. That's the way we set it up, should have gotten. But really what we want to get kids to do is to understand that substances have characteristic properties that you can test for, and you can use so that you can identify an unknown substance, as long as it's one of the ones that you've tested before. Unknown, that you haven't even tested. So one thing that we put in Inquiry in Action, let's see if I can go there quickly. Oh, go there on the website or in the book, but in the teacher background section, we have a lot of information about these substances like salt that's in there. We talk about the dissolving of salt. What else? We have not sugar, sorry, a detergent molecule to try to explain why in salt water. You have regular water, which we have water molecules. So there's a lot of feature part of here that you could talk to kids about if you feel comfortable with it, but Inquiry in Action doesn't have an explanation for students on the particle phenomena they're going to look at. It's a little more qualitative than that. But actually, we're probably on the website and try to put in some particle level explanations for kids. Things have changed. So to clean that one up, you guys, just use a paper towel to wipe it off on it at all. And if you put these caps on, try to put them on pretty really tight. And then you can pass them up front here. And then we'll our activities done. Let's move on. Maybe let me see where I am. We're still in 5th grade. Okay, let's do. Yeah, we'll have to move on to middle school now. Could you guys flip middle school structure and proper? That's this one. And yesterday we looked at, let's see. Right. Yesterday we looked at MSP. Sorry to make everybody read. This is like, I don't know if you mind, but could you, on middle school structural properties of matter, the one at the bottom, MSPS 1.
Develop a model that predicts and describes changes in thermal state of pure substance with thermal energy when thermal energy is added.
So let's see, what did we do yesterday? Oh yeah, we looked at on the wax paper to establish that, at least to try, to get the idea across that water is connected to each other. Then we put a drop of food coloring in room to get to the idea that why is that happening? It's because the particles are in motion. And then faster, and somebody suggested heating. So we looked at one and remember coloring in cold water and yellow blue food coloring in hot water. We saw that the hot water mixed faster. We want kids to reason that that must be because the particles are moving faster. You heat, that makes them move faster. So now that's part of this performance expectation. There's another part though, and it says, let's see, motion, temperature, and state of a pure substance. So they want you to get to the idea particle motion thing can even change the state of a substance. We didn't do that. We just made it move fast. An activity now about a state change. So the way chemistry and in chapter 2 is about changes of state. And let's go to this. On this set of activities with a, we always start with just some kind of engage. We tried to write these in the 5E format. I don't know if we, yeah. Everything we is according to this 5E method of writing a lesson plan. Is it? Most folks, a little? Will, do you know that? The idea is engage. Is do a demo or a little activity or have a discussion that gets everybody engaged. We're all in the, and then, hold on, don't tell me, explore. So during the engage part, you usually come up with some kind of, so then you explore. That's the second E. And that's the experiment. And then explain. And then you really want the kids to explain, but you guide them with this idea. Experiment, answer our question. Can we talk about it on the molecular, on the particles to help explain it? So that's the explain part. Then there's evaluate. Now, but this is the way we do. Explore, I'm sorry, engage, explore, extend. Just different versions. The evaluate is a formative kind of assessment using an activity sheet. So the kids are answering, writing captions to the pictures that they draw, and you go around and you look at them to see how they're doing. Kind of assessment or evaluation. We do have a more summative kind of, and then there's extend, like the idea of, okay, or with our model, can we go a little further and apply it to something that you haven't seen? Makes sense. So that's the style or the format that we use. This. So the engage part for this activity, simple. You just wet a brown paper towel and wring it out, and I squished it too hard. Then you just, I'm going to hang this up here. What's it going to be like at the end of class, do you think? Ideas? Dry. Well, why do you think that? Who said dry?
Mary Beth,
Mary Beth.
I
Well,
would think it's dry, because, you know, they close down. Right?
right. What's that? Do you know as a 5th grader what? This is middle school. Sorry. As an 8th grader, what that's called? A process, the dry stuff.
Yeah.
That's sure. Evaporation is a good. You gave the example of clothes drying. Any other quick examples of evaporation? Katie, of course. Why do I want to say Stacy? I don't know. Katie. I don't know.
Of evaporation?
Yeah, like what a kid would notice.
I don't know, I guess. Yeah,
Yeah.
like water
Sure.
dry out, yeah.
Yeah, that's a good one. How about how can you make evaporation happen faster? Like if we wanted this thing to dry out even faster, if it's going to dry out faster, what can we do?
Put a blow dryer on, heat on.
Okay, blow dryer, heat part of the blow dryer, and what you said, Katie. Why do you think that would help?
Thermal energy would be causing the particles to move more, increasing the rate.
Very nice.
Very smart experience.
You are. Notice that heat makes stuff evaporate quickly. Like, what's an example that?
Well, like a hair dryer or a clothes dryer or the sun things that like your cement dries off faster.
Does everybody agree that it seems like evaporation? How about we're an 8th grade class, we want to test this idea. How do we do that?
Have one partner just have it out in front and have another one put it on the head. Check and see if it's actually dry. And I think that it would be.
Okay, but think about that for a minute. One of the things that's wet is sitting like on a table, and wow, and mine would make pretty good contact. You would need like somebody with a cold head or a room temperature head.
Yeah, to do it.
Yeah, and head. That's going to be hard to find, I think. Well, what's another way to do it? Test to see if heat affects the rate of evaporation.
You could use lamps.
Oh, what would you do?
But kind of going off that, you could put one just with the regular light in the room. Maybe if you could put or something, or you know your storage room or something, and then do another one underneath the lamp. Just a simple.
So let's say if you had 2 things that were equally wet, and you have one providing heat, and the other one somewhere that's doesn't get any heat. You know, that's close, but you're also, light is a variable. Maybe light rate. You only want to test for heat. Is there some way to do it? You want to treat them exactly heat one, but not the other. Any ideas? Mm-hmm. And so okay, so that would make one cold, one temperature. So relatively speaking, this won't be warmer. Same idea, but have a warm pack and a cold pack. Yeah. Oh, or a hot plate maybe. Right. Or maybe 2 hot plates. 2 hot plates, one on very, very low, and then they're exposed to the same amount of light, same amount of air, and they're treated exactly, and one's not. That's good. That would work. So you have this discussion with the kids. How can we do this? You have to think of these ideas sometimes. But let's do it really quick in the we have. We're going to try to run this experiment. Let's see. If you would just hand them out to the groups, if you don't mind being a volunteer. group right here. And if you can get that group. And right there's good. You ended up on that one. I think I did that before too. Okay. I need. All right, this is, open up your bags and just take everything out, and we'll just zoom through this really quickly. Sorry, but as always. Each group needs 2 little pieces of paper, and these are, I don't know why I cut these to be that big. Thanks a lot for helping with this. This time I'll actually do 2. Okay. You're welcome. And I'll get these guys. And do you guys have your hot water? We're going to use, I came up with this idea, just a slightly different version of what she suggested, and that is make 2 packs, little, I don't know, heating pads, except we're not going to heat one. We're going to put hot. I'll show you. Can I do one? And hopefully they don't get you extra bags, but I have some extra bags. Oh, these are quart-sized storage bags. Sandwich bags are too weak. Don't use those.
Is freezer?
Yeah. And then I'm just getting rid, I'm getting rid of some of the air in the bag. Hot water in one, about up to here, and then room temperature water in the other. And so we'll set. Oh, make sure you close them really well.
Was it room temperature or do you want it?
Use room temp. But you know, you could have, you definitely could do it if you wanted. Or you could have 2 bags very cold and warm. You need to have some water to evaporate. And we want this to happen in class. So we're not going to put a petri dish of water on here or anything like that. We're going to, hold on. These pieces of paper, water on each. And then you have the discussion, right? Should we put the same, I'm sorry, I gave it away. I said 1 drop. But you would say to kids, we want to see if heat of water, so we got to use water. We're going to put water on these pieces of brown paper towel. 10 drops on one and 1 drop on another. Now, obviously, you guys, no, don't do that. So you still want to have that talk with the kids. So let's just put the same amount on both. Put 1 drop of water. And when we do that, should we put them on the pads, the warm water pad, and then wait around for a while and then put the other on the cold? Obviously, on the room temp, obviously not. So you guys, let's do this. Put your pieces of paper down on the table yet, so that when you put the drop of water in the center of each one, that we allow them equally. Then we'll put them on the bag and see if it matters. Whenever you're ready. Oh, let's put room temperature. So you can put room temperature and use your droppers to just, you and your partner, put 1 drop at the same time. In the, see what I'm saying? If you have any questions, you can ask. But we're going to run this. So, have people, you got it set up? Okay. While this is happening, was it hard? Yeah, it can be tricky. If you need new papers, right? Did it work, sort of? This is happening, you guys. Any middle school kids, I guess you don't want them around waiting for results. So we've got an animation here. Oh, not sir. Whoops. Yeah. This in middle school is early on in the year. If you were doing it chronologically, this is still. In chapter 1, you guys remember the way we showed any particle was a sphere? Now, and say, well, water isn't, it has a structure to it. And so we have the series of this is, percolating. They can look at, like, everybody knows water is H2O, but what does that mean? So we have that discussion. It's made up of atoms. And what are, you don't have to get into a lot of detail, but those H is an atom. The O is another type of atom, oxygen. So water is made up of H, of the hydrogens, and O, just one oxygen. So you give them a little something to look at. Classic look of that's called a space-filling model of a water molecule. And then if you want to, you can show this idea that remember we were saying water molecules are always in motion. So they're pretty close together, they're all moving around. So that's like a model of what water might look like if you could look all the way down at the molecules. That we suggest telling kids is that, you talk particles, think like dust particles or sand. I mean, so tiny compared to that stuff. It's okay. They'll probably think that way for maybe plant the seed that they're like almost unimaginably small. There's a schoolchemistry.com. I'll just tell you really quick. That if you took like about a tablespoon of water, actually it'd be 18 mils, but we tell kids about a tablespoon of water, and if you could count the million every second, so you'd be a super fast counter, it would still take you 100 million centuries to count all the water molecules in there. Years. That's well more than the age of the universe, as we know. Wow, they're small and numerous. So don't get the impression that they're like talcum powder, Small, you can't even kind of get it. So do we have any results talking about here? Whoops, sorry. Okay, so or drier. Yeah, brown paper towel is great. It's so that it's dark when it's wet and light when it's dry. So did you guys get the same one? It was drier. Okay. So then, we don't have time now, but this useful explanation, or ask, you don't give it, you ask the kids for it. Why would that be? How and then you want to, well, they're middle school, so in middle school chemistry, that if the particles are moving faster, they're going to be able to break away from their width. And we have some animations to show that. And then you would do draw it out if you wanted to, and you would use other models. But lots of ways to get at the particle thing for why this happened. So we always want to show them a phenomena and eventually get to that explanation. Time we have, we had some other stuff planned, but this is it. This is the way it is. Hey, you're welcome. Thanks, you guys. I'm glad you were here. If you weren't here, there's nothing to do. So to clean this one up is pretty easy. If you just open your bag into the dump container, we reuse these bags unless they're busted. Is that one? Take that one from you. And then